Hello. Hello. Okay, I think it's right. Should be all right. Hello. Am I audible?
Yes, sir.
Okay, good. Just a minute. So please enter your attendance in the chat box as usual. Enter your attendance. Hmm. All of you enter your attendance in the chat box. We'll start the class in a few minutes. And yeah, mute yourself also. Mute yourself. This. Put all my PowerPoints are ready, but I forgot to put one or two slides. Probably this was when I had to take an offline class. During those offline periods, I didn't make a proper PowerPoint. It's ready. So I want to cover at least two topics today. Well, some of your friends are still joining. Let me just put two or three more slides and then we can start. My slides are complete, but it's not. Just 2 more minutes. I think we can exceed a little bit also our period. Yeah. This completes my slides. All So I have to know that some of the slides are missing from my lecture material. Okay. So I hope the slides are visible now. All right, I think we can start here. So today I'm planning to talk about Gauss divergence theorem and Stokes theorem. See, the Stokes theorem slides was missing in my lecture notes here, so I had to put a few more slides for Stokes theorem. So Gauss theorem here, the mathematical expression is like this. So it says here that left hand side, as you know, it is a divergence, and there is a volume integration. So volume integration of divergence of a vector field is equal to, that's what it is, right? On the right side, what we have is surface integration of the vector field. So like in a mathematical statement, it says that the volume integration of divergence of A equals surface integration of A over the whole surface enclosing the volume. So that's what the Gauss divergence theorem says, and we'll talk about it. And before we talk about it here, you'll see that there is a ds vector, ds, and there is a d tau. So ds is called area element, d tau is called volume element. And well, here you can also have a, you can also assign a vector sign on top of your area element ds. So this is called area element vector, area element vector. So let me just quickly go through it, what we actually mean by all this ds vector, d tau, and all these things. So in vector integration, uh, there can be basically three types of integration. One is called line integration. Line integration. Line integration. So when we talk about line integration, if you have a certain linear or nonlinear, whatever may be, kind of curve or anything, it could be a circle also, it could be an oval shape also. If you are integrating, if you are performing summation over all this line, if you're performing summation over all this line, or maybe it's a straight line, if you're performing summation from one end to another end, in order to perform a summation from one end of the line to another end, or in the case of a circle, if you are going to perform integration from starting from one point of the circle around the circle and coming back to that point. So in that case, that type of integration is called line integration. So when you're going to perform a line integration, you need whatever vector or scalar quantity. You can perform a scalar integration also, but like we are talking about vector analysis here. If you're going to perform a vector integration here over any this kind of line, what you are going to need is what we now call it as a line element, dl, line element vector, in fact. So if you're going to perform vector integration, it's going to be line element vector integration over this. And there has to be a dot product, scalar product between these two quantities. If you're going to perform a scalar field integration, it should be simply like this, without any dot product and without any vector sign here. So what is DL here? DL is called line element. So line element, when we talk about element, we are talking about an infinitesimally small quantity or small segment, infinitesimally small segment of that line. This is called your DL. Okay. Over here, you can take any line element here. This is your infinitesimally small segment of the curve where you're going to perform the integration, infinitesimally small segment. And the reason why we are considering this DL line element to be very small is that when you're going to perform a vector field integration here, the vector field A vector, it can have different magnitude, it can have different orientation at different places. So in general, if we talk about any vector field, you can have a vector field which is varying in over the space, which is varying over the space, which can have a variety of direction and which can have a variety of magnitude, right? So what basically you are doing here is that you are summing this vector field from one end of the line to another end of the line. In order to perform the summation, we have to consider this line element, and the line element has to be so small so that the vector field A vector here is uniform. The vector field A vector here can be considered uniform or constant over such small segment. Okay, the vector field can be considered uniform or constant over such small segment, so that when you perform this integration here, you can simply consider DL to be non-varying, A vector to be non-varying over this DL element, right? So, and with the help of this, what we are going to do here is that when we write A dot DL, this will give me the value of A over this small segment. But when you are performing the integration from, let's say this is let's say this is L equal to 0, let's say this is L equal to capital L, so 0 to L, that means you are summing the contribution of this vector field over each and every line element, the contribution of this vector field over each and every line element from L equal to 0 to L equal to L. So that's how it is, right? And here this element, this small segment, infinitesimally small segment, is also sometimes given a vector. The vector sign is given because this line element vector is considered to have a direction which is along the tangential direction. So if you take this kind of curve like this, what is the line element DL vector direction over here? You are saying that this is a vector quantity, it should have a direction, right, in addition to the magnitude. So the direction of the line element at any point along the curve is, you just take a tangent over there. If the integration is from left side to right hand side, you just take a tangent at that point along the right hand side. The direction of this tangent will give you the line element vector direction. But over here in this circle here, if you're going to integrate in this clockwise direction, if you're going to perform clockwise direction integration, you have to take it, what is the line element vector here? Just take a tangent vector here along this direction. This will give me the line element vector at this point. But if the integration is to be performed anti-clockwise along this direction, if you're going to perform along this direction, you can just take a line element here anywhere along the circle. You just take a tangent along this direction, not along this direction. So along the direction of rotation, or along the direction of integration, that is anti-clockwise direction, you have to take a tangent, and the tangent vector at that point will give you the direction of the line element vector. All right, that's how we do it. And here we also see that there is a term called surface element. Surface element. So if you are going to perform integration over a certain surface like this, so this is surface, whatever, it can be a flat surface, it can be a curved surface, or any irregular surface. Also you can perform integration of the vector field over that. So over this surface you may have a vector field A of this magnitude, A in any direction like this. So you have to consider, in order to perform a summation like this, summation of vector field A over small area, you have to perform, if you perform a summation of vector field over small area, this is called A dot ds. So ds is taken very small. The magnitude of ds is taken very, very small, infinitesimally small. So if ds vector magnitude is very, very small, then you can see that the area vector can be considered constant or non-varying over such small infinitesimal area. But if you consider a small, a larger area vector here, over here the vector field may have a direction like this. Over here the vector field may have an arbitrary direction like this. So you cannot consider a large area element, because the vector field A itself will be varying over such a large area. So therefore, when we are going to perform a summation, usually we start with infinitesimally small area element here. So that infinitesimally small area element is taken to be very, very small, such that A can be considered to be uniform or constant within that. And here, that area, you know that area is a scalar quantity, but in vector analysis, area can be considered as a vector. So the way we consider area as a vector is that we consider area as a uh, area or surface element vector. We call it surface element vector, or sometimes we call it area element also. It doesn't matter, it depends on your preference. So even though its area is a scalar quantity, we assign it this area element as a vector quantity. The reason is that when we are going to perform a surface integration of this vector field, we need to convert this we need to engage this into dot product between these two. And this area vector, what is the direction? Now the question is, what is the direction here? Area vector ds vector is for any surface expressed like this. Ds is the magnitude of this area vector. This is simply the magnitude of the area vector, infinitesimally small area magnitude. And we consider unit vector n cap. N cap out here is what we now call it as a outward unit vector. Outward unit vector. Outward unit vector normal to ds. So like if you have an enclosed surface like this, for example, enclosed surface like this, so this is your ds area element, infinitesimally small, and your n vector has to be outward from this enclosed surface and also normal to the surface it represents. Okay, so your n vector is a unit vector. It's a unit vector. It's a unit vector means magnitude of n cap is 1, and the direction is perpendicular normal to the area. Its direction is perpendicular to normal to the area, and it is outward from the surface if it is enclosed surface. Okay, that's how we use this area element. And in addition to that, if we are going to perform volume integration over the volume enclosed by this arbitrary surface, you have to consider volume element again. Okay, you have to consider volume element again. So the volume element, it is called d tau. So this volume element is called d tau. It's an infinitesimally small volume element. So that within this volume, your vector field can be considered uniform or constant. So first we assess the value of this A over such small volume element, and then we move this volume element along this direction, along this direction, along this direction, so as to cover the whole volume of the whole volume enclosed by this surface. So this simply A d tau will A d tau will perform the assessment of or the summation of A within this volume element, the value of A within this volume element. And if we move along this direction, then we are summing up the value of A vector field along this rod and along this direction, So that's why that's how we perform a vector integration. Okay, so this volume element, it doesn't have any, we cannot assign any vector. So d tau is always taken as a scalar. Okay, volume element, volume, we cannot assign any direction here. But line element, we can assign a vector. We call it line element vector. And here area element or surface element, also we can assign a vector. So that vector will have a direction normal to the surface it represents. That's what we need to know about the basics of this vector integration. Okay, so what is the physical meaning of that Gauss divergence theorem over here? And on the right hand, on the left side, we have divergence of A. Divergence of A, when we talk about it last week, we said that divergence of A, like when we calculate the divergence of vector field, the vector field the divergence of vector field is finite or non-zero when you have a vector field which is having net outflow or net inflow, right? So divergence of a vector field, it will represent the net outflow of a vector field over a certain volume. So if you have a certain volume like this, when we say divergence of A measures the net outflow of the vector field. And if you are integrating over a volume like this, d tau, you are summing the total outflow of, the vector field, total outflow. It can be outflow or it can be inflow, right? Either it can be outflow or inflow. So this will simply gives you the either the total outflow or the total inflow of the vector field over a certain volume, right? And here in this Gauss divergence theorem, V is the volume enclosed by the surface S. So if you have a closed surface S, V is the total volume enclosed. See, V is the volume bounded by a closed surface S, right? So uh, here on the right hand side, you are performing integration of this A dot ds over the surface here, over the surface that encloses the volume V. So the left hand side gives you the total outflow of, or the total inflow of the vector field A, and the right hand side, what it gives here is A dot ds. A dot ds is a measure of the density of A dot ds is a measure of density of vector field A. It's a measure of density of the vector field A. So A dot ds simply means that this is what we also given the term A dot ds, which is a measure of density of the vector field A. The term given for such measure of density of the vector field A is called flux. So A dot ds is the, like suppose you have a certain surface element here, ds, A dot ds vector will give me the flux over this surface element. But when you perform the surface integration over the whole surface, then you are summing the flux over the surface, you are summing the flux over all the surface of this surface S. So here on the right hand side, what it gives is the total flux. Or the right hand side will give you a measure of how many like the density of the vector field over the whole surface. You're summing the flux over the whole surface, right? So what it means here is that this is the net outflow or inflow of the vector field from the volume element. So this left hand side measures the total outflow or the total inflow of the vector field. However, the right hand side of the divergence theorem measures the total flux across the surface S. So you have any irregular surface, closed surface, it simply says that whatever outflow or inflow of the vector field you have from a certain volume will be same as the number that will be same as the total amount of the vector field crossing the surface. So okay, so that's what it is. Now let's discuss this problem. So here it says that verify a divergence theorem for vector field A taken over the region bounded by this. So the region bounded, the region under consideration is bounded by this surface and this surface and this surface. So you remember here surface, the general equation of the surface, we represent it like this: phi equal to c. Phi can be a function of x, y, z. So here we consider three surfaces. One surface is this, another surface is this, another surface is this. So the first surface here is x squared plus y squared equal to 4. And what is phi here? phi over here will be x square plus y square, and your constant is 4, right? The second surface we consider here is z equal to 0. So here your phi is z. And the third surface we consider is z equal to 3, and here your phi is also z. Okay. So this is how we consider a surface equation phi equal to c. Phi is this is the equation that represents any surface in general. So what is this surface here? X squared plus y squared equal to 4. So x squared plus y squared equal to 4, you know this. This is an equation of a circle, right? Equation of a circle. What is the radius? Equation of a circle of radius 2. Now, if we consider this as a surface, this will simply represent an infinitely long circle having what is the circle on? The circle is on the xy plane because x and y coordinates are here. So this will represent a circle on the xy plane, something like this. So circle of radius 2. The radius here is 2, radius here is 2. But if this is going to represent a surface, this will represent an infinitely long cylinder. Okay, this is your z-axis, this is your x, this is your y, infinitely long cylinder of radius 2. So x squared plus y squared equal to 4, though it's an equation of circle. So this particular one can represent any circle like this. It can represent any circle like this. So it could represent infinitely long cylinder of radius 2. Now, what is z equal to 0? Z equal to 0 is the surface on the xy plane. So this particular plane on this is z equal to 0. So this will be your z equal to 0 plane. Okay, because for every point on this plane, z value is 0. Z value is 0 for every point on this plane, right? Now, what is z equal to 3 surface? Z equal to 3 surface. This is z equal to 0. This is z exists. So let's say this is z equal to 1. This is z equal to 2. Z equal to 3. So over here, cutting this z equal to 3. Let me construct another plane here, something like this. You just imagine another plane passing through the z axis at z equal to 3. So if you consider such plane which is parallel to the xy plane, passing through the z-axis like this, for every point on this plane, z value is 3. You take any point here, z value will be 3. Why is that? Because you are considering a flat plane passing through the z-axis and parallel to the xy plane. That means for every point, if this flat surface passes to the z-axis at z equal to 3, then every point the value of z is 3. So z equal to 3 defines the equation of this plane. So you have one infinitely long cylinder of radius 2. You have two planes like 2 z equals 0, 0 and 2 equals z equal to 3. And what is the surface? Here the question says, what is that? Taken over the region bounded by these three surfaces. Okay, so that means you have one surface and you have another surface here. So the region which is bounded by these three surfaces will be over this. I hope you can capture what I'm trying to convince you here. So you have one infinitely long cylinder. You have two plane surface cutting the cylinder. Z equal to 0 is cutting the cylinder here, and z equal to 3 is cutting the cylinder again over here. So this is your volume under consideration, the volume enclosed by these three surfaces, right? The volume enclosed by these three surfaces, the volume under consideration here. So I hope you can understand when we represent this using this figure. So you can see that we have to verify divergence considering the volume bounded by these three surfaces. All right, so the volume bounded by these three surfaces will be like this. Now, Here, in order to verify divergence theorem, what we're going to do is we're going to perform the left hand side of divergence theorem. We have to verify that the left hand side of divergence theorem equals the right hand side of divergence theorem in this particular problem. So the vector field is given, it is this quantity. And let us first start with the left hand side, that is volume integration of divergence of the vector field. So in order to do that, let us take the divergence of the vector field. This we know it, we have already done it. Del operator is this. So when you perform a divergence and all, please do not forget to put the dot product sign. If it's going to be a cross product, put a cross product. If it's going to be a dot product, put a dot product. This in vector analysis, putting a dot and cross and representing or putting a vector sign. So putting a vector sign over here on top of this del and on top of the vector, and also putting a small cap. So whenever you put a cap here over a letter, this says that this is a unit vector. All right. So in vector analysis, this has to be taken care properly. If you are missing this vector sign and notation and all, then your calculation is probably meaningless, and moreover it will lead you to wrong results. So divergence of a, this is a vector a, so I dot I cap is 1, because we already know it, right? I dot I cap dot product between the same vector is 1, because the magnitude is 1, magnitude is 1. Cosine of the angle between them, cos 0 is 1. But if you take a I dot j, this will be the magnitude of I is 1, magnitude of j is 1. So magnitude of I, magnitude of j is 1. Cosine of angle between I and j, because they are orthogonal vectors, this is 90 degree. Here I, you know that this is unit vector along x-axis is I cap, unit vector along y-axis is your j cap, unit vector along z-axis is your k cap. So there is a 90 degree between them, so cos 90 is 0. So following that, you can simply say that j dot j is 1, k dot k is 1. Otherwise k dot I, k dot j and all are 0. So this will be like differentiation of del 4x upon del x. So 4 is a constant, so del x upon del x is 1. So this is how you get 4 here. So I don't need to explain all of this. So there is a minus 2 here. Del y square upon del y will be 2y. 2 into 2 is 4. So I hope you understand the rest of it, right? So please perform this differentiation. This is what you should get. Now the volume element over such volume, we call it, we consider it as a d tau. Okay, d tau. And this is the Cartesian coordinate system we are using, x, y, and z. So the d tau in a Cartesian coordinate system is simply dx, dy, dz. Because here, when we write a volume element like this, you just consider it infinitesimally small rectangular, rectangular or cubic box like this. Along this axis, the element is what we call it as dx. See, this is your x-axis, this is your x-axis. So along this axis, the element is dx. This horizontal is your y-axis. So along this line, the element here we call it dy. Along the vertical line, this vertical line is your z-axis. So along this vertical line, the element here you call it dz. So the volume of such infinitesimally small box will be dx, dy, dz, just a product of the 3 dimensions, right? So it's like you have length, you have breadth, and you have height. So if you have such kind of box, in order to find a volume, length, breadth, and height product, this will give you the volume. So similar to that, infinitesimally small volume element, dx, dy, dz will be the element, your d tau. Okay, so instead of d tau, on the left hand side, we write simply dx, dy, dz, and you have to perform this integration. And in order to perform this integration, what we're going to need is that we are going to perform the summation of the summation of divergence of the vector field over the volume enclosed by the 3 surface, this surface, this surface, this surface. So the volume enclosed by this surface is as represented here. All right. So in order to do that, you have to take the limit for x, y, and z such that you are able to cover the whole volume. So you cannot take the limit x, y, and z arbitrarily. You have to consider the limit for the integration x, y, and z so that you are moving over the whole volume, not beyond the whole volume, not less than the volume. So you have to perform the integration, the summation within such volume. Right. So in order to do that, you know that let me just quickly draw it once again. So this is z equal to 0 surface, and this is z equal to 3 surface. So you just consider a small rectangular box, something like this. This is your infinitesimally small volume element. So if you perform integration from z equal to 0 to 3, that means you are summing this small box from z equal to 0 to, you are summing along this direction up to z equal to 3. Okay, when you perform z equal to 0 to 3, this d tau, this is your d tau. That means you are summing d tau from z equal to 0 surface to z equal to 3. So if you perform this z integration, you will now have a rectangular rod, something like this. You will now have a rectangular rod, something like this, right? And now you have to perform integration along x and y. You know that the radius of this circle is 2. So the equation of the circle is x squared plus y squared is equal to 4. So what you have to do is y equal to square root of, here this will be 4 minus x squared. So when you perform a square root over that, it can be plus or minus. All right. So if you use this equation to consider the limit for y, because taking a square root over any quantity is either plus or minus, right? So you can use this integration, sorry, this equation, the equation of the circle, here. You can perform the integration from minus of square root of 4 minus x squared to plus of square root of 4 minus x squared. So what that is going to give you is that, yeah, you are going to move this rod, rectangular shaped rod, from one end of the y to another end of the y. You can move from this to this, you can move from this to this. It can take you anywhere along this summation, along the horizon, right? And then here you see that see the radius of this circle is 2. You know that. So this is behind axis. The behind axis is called minus x axis. The front axis is called plus x axis, right? So at this end, x value is 2, and on the behind axis, where the circle cuts the x axis, the x value will be minus 2. So in order to perform the integration over this volume, the limit for x has to be chosen from minus 2 to plus 2 again, so that it will cover the whole volume, right? So I think I have spent too much time on that. So by choosing such limit, you just perform a simple mathematical integration. So as I said, first you perform the integration with respect to z. Z integration is to be performed first, and then to the y integration, and then lastly x integration. So this is what we do. First perform the z integration. So I think I don't need to explain this kind of integration calculus and all. Please revise your class 12 mathematics. You have already studied this calculus. Just my duty here is to explain the methodology, how you have to take the limit and all. So, but this kind of simple integration, let me skip it. So anyway, you perform this integration or revise your calculus. So once you know the limit of integration, you just first perform with z, and then with y, and then with x finally. So this is the step you should take. And like, you know that over here, just one thing which you already studied in class 11 and 12, if you have any even function means f of minus x is equal to f of x. This is called even function. If you odd function means f of minus x equal to minus of fx, this is called odd function. Okay, so if you have an even function, if you have an integration limit from minus a to plus a of such even function, this is simply 2 times this. But if your function is odd, if you are going to perform minus a to a, the integration will be uh, uh, this does not equal this. Okay, only for even function, integration from minus a to plus a is equal to 2 times 0 to a. Otherwise this is not equal to this. Okay, for odd function is not equal to this. So even function means you just put f of minus x over here. So the function you're going to perform the integration is this. So you put f of minus x. So minus x square is plus x square. So f of minus x is same as f of x, right? So this is an even function. If it is an even function, then you can write minus a to plus a integration as 2 times 0 to a. So you just follow that. And also this is integration of a square root. And from the trigonometry law here, you can see that you have to substitute x as 2 sine theta like this, so that whatever within this will be 4 minus 4 sine square theta, and you can write this as 4 times 1 minus sine square theta, and 1 minus sine square theta, you know it, this is cos square theta, right? So this can be written as 4 cos square theta, and there is a square root here. So square root means 2, cos square means cos theta. So 2 cos theta, you can convert it to 2 cos theta. So for simplicity, you have to use a substitution method using this trigonometric property to simplify this square root integration. This you already studied in class 11 or 12 class. So all these things, if you follow that, finally you will get this as a 84 pi. All right, I almost finished. Oh, I think I was thinking of covering Stokes theorem also, but I don't think I would be able to do in this class. Anyway, so this is the left hand side. This is what we get out of volume integration of divergence of the vector field. Now on the right hand side, what we need to execute this surface integration of the vector field A. That means this is the total flux over the surface S. So as we often discuss, the surface can be split into 3 surfaces, S equal to 1, S1, S2, and S3. Okay. So like this here, let me just draw again. This is X, this is Y. Just try to picture the surface here. Now we are going to perform the surface integration. So this is S1, and this is your second surface. The third surface is the surface S3 like this. So if you look at this S1, at S1, the equation of the surface is z equal to 0, right? Z equal to 0. So your phi is z. So you can find out the normal to the surface using grad phi. Grad phi is the normal to the surface. So you just take a grad of that z, then this will be equal to k cap, because k cap into k cap is 1. Del z upon del x is 0, del z upon del y is 0, del z upon del z is 1. So you get k cap. But you need to consider, for a surface element, you need to consider an outward normal vector, right? So outward means this is the volume you enclose. So the outward to this will be along this downward direction. So upward direction is your k cap. Unit normal along the positive z axis is your k cap. Unit normal along the negative z axis will be minus of k cap. Minus of k cap is your unit normal, right, along the negative z axis. So you just put all these values, and then I know that if you're going to perform the integration of this vector field, over here, look at this. This is what we are discussing. Integration of the vector field on this surface z equal to 0. That means you have to put the vector field. The vector field on this surface will be like this, because on this surface your z value is 0, right? Put z equal to 0. Then you take a dot product a dot n. This is what you're going to get. Your n cap is direction is n cap is this, n cap outward unit form normal vector is minus of k cap. So your a vector is this. So the product is 0. So if this is 0, a dot n is 0, this quantity is also 0, right? And look at this. This is your surface S2. So the surface S2 over here, this is the surface. You're going to perform the integration of the vector field uh, over this surface. So over this surface, your a value will be such that, what will be your a value? A vector will be 4xi cap plus, sorry, 4xi cap minus 2y square j cap plus z square. Here over the surface, the equation is z equal to 3. So over the surface, that value is 3. So 3 square k cap. 3 square means 9. All right. So this is what you will have as your a vector, and the unit vector, outward unit normal vector to this surface is your k cap here. So you just put n cap plus k cap, and then k cap equal to k cap. K cap dot k cap is 1, k dot j is 0, k dot I is 0. So then this is 9, and a dot n vector is 9. So 9 is a constant. You can take it out of the integration. Now what is left here is this. So this ds vector, ds element, this ds2 is a surface element, a small infinitesimally small area element here. ds2 is an infinitesimally small area element here. Now you are summing this ds2 over the whole surface like this. You are summing ds2 over the whole circular surface. If you are summing this ds2, this is what it does. ds2 is a small infinitesimally small, very sorry, it's my time is up. This ds2 is, till what time we have a class? 10:15, right?
Yes, sir.
Yeah, I think just 1 minute. Yeah, 10:15. You're going to have class at 10:30 again. So ds2 is a small area element. So if you are going to perform the integration over this s2 is a surface, the circular surface. That means you are summing this area element over this circular surface. If you are doing that, then finally what you're going to have is area of the circle, right? Area of the circle. Area of the circle. So what is the area of the circle what is the radius of this circle? The radius of a circle is 2. Radius of circle is 2, right? Area of the circle is pi r square. Radius of circle is 2 pi 2 square, right? So this is what you have, pi r square. So radius of circle is 2 there, so 2 square 36. So this is what you get. Okay, so I think I should stop here. We have to continue with the integration of this, and hopefully I can take class tomorrow, sorry, tonight, because I don't want to have a long gap in between the same topic here. So if you allow me to take class at 8 p.m. tonight, I think we can finish this particular calculation, as well as Stokes theorem and Green's theorem. So vector integration, I want to complete it this week, because if we wait till next week, then you would forget most of the things we discussed today. So let's take class at 8 p.m. today. Okay. All right. Let me stop there. Have your next class. Enjoy your day.